Okay, so we're very happy to have Marco Mazzucchelli from Paris here on site, and he's going to tell us about a few properties of Besse contact manifolds.
Thank you very much for inviting me to Paris. It's very refreshing to meet like a real human being. Another feeling. My talk was really improvised. I'm going to do a recollection of a few recent results on Besse contact manifolds. I believe I spoke about Besse contact manifolds. It was not the same talk. Here in Paris, the very last talk that I gave in my life on time. This is based on recent joint work with Marco Radeschi from the University of Notre Dame, not Notre Dame in Paris, Notre Dame in Lyon. And
it's hard to understand.
Is it because I ask, or?
I don't know. It's hard to understand what Marco is saying.
Okay. So,
so the sound is not good, my friend. We should do something about the sound.
Should speak slower, maybe, or it's really a problem of hardware?
No, I think it's just like the audio in the room is a bit. I mean, at least for me, I don't know about everyone else, but I mean, just maybe go on.
Okay. Is he saying that audio like that, or is he saying that?
He's saying that then the sound is not good. So we start again for good.
Thank you.
And we're going to listen to Marco Mazzucchelli from École Normale Supérieure de Lyon, speaking from Paris about Besse contact manifolds. Thank you.
Thank you. Sorry for the unexpected. I was saying that this talk will be a recollection on recent results and work in progress on Besse contact manifolds, which I'm going to recall at the beginning of the talk. And so the talk is based on recent joint work with Marco Radeschi from University of Notre Dame, and second project, which is a work in progress, more or less completed, with Alberto Abbondandolo and Christian Lange, who is a postdoc in Munich. So, so it will be a talk about contact manifolds. So let me set up my notation. So we'll be denoting contact manifolds by Y of general dimension 2n-1, and mostly the dimension would be 3. Not mostly, but for the second part of the talk, let's say. Lambda will be a contact form, and I will denote by phi lambda t the Reeb flow. I wrote here the definition, although at this seminar, pretty much everybody is very familiar with the contact geometry. So a contact manifold, closed and connected. I always forget to write. All my contact manifolds will be closed and connected. Certain things are wrong if the manifold is not connected. So, so a closed connected contact manifold is called Besse when all its Reeb orbits are closed. Every orbit is periodic. And a typical example that we'll have of, you don't see the highlight. The typical example of Besse contact manifold we all have in mind are the rational ellipsoids. So this is my notation. So we'll denote rational ellipsoid by E of A1, AN, where A1, AN are positive parameters. They're usually chosen so that A1 is less than or equal to A2 and so forth. So for me, an ellipsoid would be a solid ellipsoid. So it's a set of points in Cn, Z, such defined by this inequality, normal Zj squared mod Aj. If you sum over all the j, is less than or equal than 1/pi. So with this convention, which is the usual one in symplectic geometry, you always have n periodic orbits of period equal to the AI. Periods equal to the AI. So, this is on the boundary of the ellipsoid, which is a close contact manifold that comes equipped, it's convex, so it comes equipped with a canonical contact form, which is the one that I wrote down here in complex coordinates. The real coordinates is the usual 1/2 x dy minus y dx. So this is contact on the boundary of the ellipsoid, which would be a non-solid ellipsoid. And the Reeb flow is a linear flow that rotates each factor separately with angular velocity 1/aj. So So this would be just an ellipsoid, and the ellipsoid is rational when any quotient of two parameters is a rational number. Okay, so you see that here, under this rationality condition, all orbits close up after a period which is the least common multiple of the AI. Okay, so this is all very, very classical. So let me mention that it's a theorem due to Watzley, and it's a classical theorem from the 1970s, that the Besse red flow is itself fully periodic. Namely, the time tau map of the Reeb flow is the identity for some tau positive. And so this theorem is classical, but it's actually not elementary. It's quite subtle. And if you drop the assumption of the flow being Reeb, the theorem is wrong. So there's an example due to Dennis Sullivan, possibly even more examples, but the first one was given by Dennis Sullivan of a vector field on a closed manifold, all of whose orbits are closed, but there's no common period because the periods are unbounded. Somehow the Reeb condition forces to have a uniformly bounded period, and once you have a uniformly bounded period. So Watzley theorem is a consequence of the fact that Reeb flows are geodesical. So the Reeb orbits are geodesics for a suitable associated Riemannian metric. So Alberto already spoke this morning about Zoll contact manifolds, but let me remind you the definition. So a subclass of Besse contact manifold is called Zoll. This is there's a subclass of the Besse contact manifolds called the class of Zoll contact manifolds. And those are the contact manifolds which are Besse, so all of whose Reeb orbits are closed, but every Reeb orbit has the same minimal period. So the same tau for all the orbits. And
what is the difference between Zoll and Woodby1?
Zoll and Woodby1 is the same thing. The terminology you should say is not, thanks for asking, maybe I should point out. They're usually called Woodby1, say in Ivy's book, for instance. And they're called Zoll in the systolic literature because of Zoll Riemannian metrics. It was the first exotic ones was given by, for example, due to Zoll. So this terminology picked up with the recent work of Alvarez Paiva and Balashov, and then Alberto and many other authors. And Besse is, I don't know who used it for the first time, but the name is due to since you're based in France, Besse's monograph, Manifolds, all of which geodesics are closed, which deals with Besse unique cotangent bundles. And Besse is a pseudonym for a collective of French authors, including Marcel Berger, Bourguignon, I believe, René Michel, Jacques Lafontaine, and many others, and a few others. Okay, so typical example of Zoll manifolds, round spheres, so the ellipsoid with all parameters equal. And even before round sphere, historically, the very first example was the unique cotangent bundle of, say, the round end sphere. Okay, so this class of contact manifolds, Besse and Zoll, these two classes, are remarkable for many reasons. And in this talk, I want to do a recollection, as I said, of the main properties. So here's a relatively recent theorem that I proved with Cristoforo Gardiner. It's not the first theorem in this direction, but it was a bit of a final theorem in dimension 3. So point 1, I spoke a few times about point 1, so some of you may already know. So being Besse for a close contact connected 3 manifold is the same thing as asking that its action spectrum has rank 1. So it's contained in the multiples of a given positive number. So the action spectrum, which I denote here by sigma, it's just a set of periods of the Reeb orbits. And when I say period, I mean all the periods, not necessarily the minimal ones for every closed Reeb orbit. And so I put here these 2 points together, so this is a non-trivial theorem. It requires embedded contact homology, and even in, say, standard settings, like convex hypersurfaces in the symplectic vector space or geodesic flows, even in settings in which there's other technology available, I don't know how to prove it. Somehow the spectral invariance from classical Morse theory are not good enough for this statement. So the second point is actually a bit unrelated from the first, if you state it this way, and it's actually more relevant for this talk. It has nothing to do with, its proof has nothing to do with embedded contact homologies, much more elementary. It says that two Besse contact forms, lambda 1, lambda 2, on a three-dimensional closed manifold are strictly contactomorphic if and only if they define the same prime spectrum. Now, there's a bit of terminology, although quite standard. So the prime spectrum, it's the collection of the minimal periods of all the Reeb orbits. Every Reeb orbit contributes with its minimal period, but not necessarily with the multiples. So this gives more information on the spectrum. And strictly contactomorphic, as usual, means that there's a B field of Y that pulls back one contact form to the other. So this is essentially an application of the classification of cipher fiber spaces. I didn't mention it, and I won't really spend much time on it, but three-dimensional Besse contact manifolds are cipher fiber spaces where the vibration is given by the action. The S1 action is given by the Reeb flow, thanks to Watt's-Lee theorem. So combining point 2 of this result with a classification of cipher vibrations, which is it's a classical topic, but actually for spheres and length spaces, it's been completed only recently by Ensor Geiges and Christian Lange. So I said, by combining this classification with point 2 of the theorem, we get this corollary, which says that every Besse three-sphere, all of whose Reeb orbits are closed, is a rational ellipsoid up to strict contactomorphism, obviously. And so this corollary, I don't know if it holds in higher dimension, and actually, I don't know if it holds even under restrictive assumptions, like for say, convex hypersurfaces in a symplectic vector space. Indeed, as Alberto pointed out to me, Alberto Abbondandolo, it's not even known if there are exotic Zoll spheres in higher dimension. And this question seems difficult to me. It's actually related to the uniqueness of symplectic forms on complex projective spaces. So we know that CP1 has a unique symplectic structure once you normalize the volume, say, because it's a surface. For CP2, the uniqueness is a difficult theorem due to Taubes. And if I didn't miss anything recent, nothing is known for dimension 6 on. Okay, so stop me if you have questions, of course.
Yeah, I have a question. So can't you prove then some kind of classification in dimension 5?
How do you prove a classification in dimension 5? Which classification?
I mean of Besse contact manifolds on S5, because then the quotient is indeed CP2, and you know it already, the symplectic performance. You may know this corollary in dimension 5 thanks to Taubes. I forgot, but there may be a subtlety. But it may hold in dimension 5. So let's say that this is completely open in dimension from, say, 7 on. Yes. But yeah, you're right. I should look at into dimension 5. I don't think it's enough, although, to use Taubes. Maybe there's something else needed. I think about it. I actually thought about this for a while, but I forgot what was the conclusion. Yeah. So. More questions? So as I said, I cannot answer this question in, say, arbitrary dimension, not even for Zoll spheres. So the first theorem that I'm going to present today goes in the direction of answering yes at this question, although it's still a long way to say yes. So my first theorem will show that there's some resemblance between Besse spheres and rational ellipsoids beyond the obvious. So in order to introduce the theorem, let me spend a few words on classical properties, the simple properties of Besse contact manifolds. I already mentioned the Watt's-Lee theorem. So here's another property. So you have a Besse contact manifold Y. And for every value of the action spectrum, say A, I'm going to denote by Y index A, the subspace of aperiodic Reeb orbit. So a priori, this is possibly this is a compact subspace of Y because it's a fixed point space. But more is true. This is actually it may be disconnected, but every connect may be disconnected, and the components may have different dimension. But every component is a nice smooth submanifold, and it's actually a contact submanifold of Y. So this is a little exercise on, say, fixed points of isometries. With the right Riemannian metric, the Reeb flow becomes an isometry. Every time T-map of the Reeb flow is an isometry. Furthermore, Besse contact manifolds are Morse-bot. This is also an exercise. Morse-bot means that the dimension of this subspace of aperiodic orbits is equal to its nullity as a periodic orbit, which is the linear algebra quantity that I wrote here. It's the usual notion of nullity, say from dynamics. And pretty much for every reasonable variational principle you have for closed Reeb orbits, this tells you that the functional is going to be Morse-bot. So this is all very, very classical. So now let me focus on convex contact spheres. For the first theorem will be for this class. So let me just set up the notation, the terminology. So Y is a convex contact sphere when it's a hypersurface of the symplectic vector space Cn, diffeomorphic to the sphere and actually with positive sectional curvature. And it's customary to this is not very important, but it's somehow customary to require that the origin is enclosed by the sphere. So it's contained in the interior of the compact filling of the sphere. And with this choice, there's a canonical contact form on Y, which is the same one that we used before for the ellipsoid. It's 1/2 x dy minus y dx, which I wrote here, complex coordinates. As I said, we don't know if Besse spheres are necessarily rational ellipsoids. And actually, I don't even know it for convex contact spheres, for Besse convex contact spheres. So the first theorem shows that it still has a few things in common with convex contact spheres. So here's the first theorem. So let me first read the theorem, and then I need to make some comments about it. I need to speak, So theorem says that if you have a Besse convex contact sphere Y, then you look at its subspaces, what I called before YA, which I remind you is the subspace of aperiodic Reeb orbits. Now, each of these subspace, which we know it's a collection of contact submanifolds, is indeed connected, and it's actually an integral homology sphere. Now, at the beginning of the story, we thought that this theorem would actually follow from general results on circle actions on spaces, on manifolds. And this is a very classical topic, very mature. There are all sorts of results. So we took the book by Breton, which is one of the Bible of the subject. You can find Breton's book easily on Amazon for less than 300 euros. Anyway, you go through the book, and there are plenty of results that tells you how the subspaces of fixed points of subgroups of S1 look like. There's nothing like this. And there are even exotic S1 actions in which the certain strata, certain YA are very different from spheres. We thought that this theorem would follow from Schmidt, the classical Schmidt theory, but it doesn't. Schmidt theory tells you something about strata which are fixed by ZP, where P is a prime. ZP is a subgroup of the S1 that is the Reeb flow that acts as a snap. Okay, so this was the comment on the statement. So let me maybe say a few words. Let's see how it goes with time. Yeah, I say a few words. I don't want to spend too much time on this proof. I actually spoke about this in Lisbon about a month ago. And in case you're interested, you can write to me, or you can also find the video on the Lisbon website. So the proof is inspired by a recent beautiful result of Marco Radeschi, my collaborator, and Wilkin, that solves the Berger conjecture for Riemannian spheres. Berger conjecture says that a Besse Riemannian sphere, so meaning that its unique cotangent bundle is Besse, is necessarily Zoll. And Radeschi and Wilkin proved it for all spheres, except oddly for S3, which for strange reasons, their proof breaks down. But I believe that the feeling is that it should hold for all sphere. There's nothing special in S3. For S2, it was a theorem of Grommel and Grove. So inspired by this proof, I'm going to employ the Clark action function as it's customary for convex contact spheres. And let me go a little fast because I won't really give much detail on it. But say Clark action functional is a well-behaved functional defined in a certain domain, which is pretty much an infinite dimensional sphere, sort of, up to S1 equivariant homotopy equivalence. And so we know the topology of its domain. It's pretty simple to describe. And the core of the proof is these 2 points, both of which are actually highly non-trivial. So I start from the second one. Well, actually, let me start from the first. So we already know that the Besse contact sphere is Morse bot. And first point was to prove that every critical manifold is actually homologically visible. Its negative eigenspace is orientable. And this is something that's quite elementary for Zoll spheres, but it's difficult, or at least we couldn't find an easy argument for Besse spheres. It's symplectic linear algebra, but for my standards, not so easy. And the second property, second property says that the Clark action function of the Besse convex sphere is perfect for this one equivariant Morse theory. Once again, this is very easy or relatively easy for Zoll spheres, but for Besse spheres, it's difficult. And it actually uses, for the first time in my life, it uses the torsion of the S1 equivariant homology in a crucial way. Somehow torsion has always been a source of mistakes in the field, and usually we tend to quotient out the torsion. Here the torsion is crucial. Without the torsion, I couldn't prove this. Okay, so I won't say much more on the proof, but out of these 2 points and the knowledge of the domain, the theorem follows from, let's say, usual Morse theory. Once you have these three ingredients. And okay, so actually what we were interested in was the next theorem, which is a corollary not of the previous theorem, but of the proof somehow. And next theorem says how to compute the Eckland-Hofer capacities of a Besse convex contact field. So let me remind you what these capacities are. So if the capacities are, say, numbers, sequence of numbers introduced by Eckland-Hofer in the early 1990s or late 1980s. They're denoted by CK, and you can associate them to any, say, compact subset of Cn, also non-compact, but let's say compact for this talk. So CK of B is the kth Eckland-Hofer capacity, and the properties they have are the following. I'm not going to mention all their properties. Their constructions, it's a min-max, which is a little bit involved. There are actually several recipes that are more or less equivalent. But so first property, among the most important, the CK are symplectic invariants, monotone under the inclusion, therefore monotone under symplectic embedding, and one homogeneous. And C1 is an ordinary symplectic capacities as the one that they're usually employed in symplectic geometry, meaning that C1 of, say, the unit compact ball in R2n is the same as C1 of the unit ball in R2 times R2n minus 2, which is the symplectic cylinder, unit symplectic cylinder, and both capacities are equal to pi. So next property, which was considered a bit of a miracle when they came out, is that these capacities are actually action selectors. This means that if you have a compact domain in Cn with smooth and restricted contact type boundary, So it's contact type with respect to a primitive of the symplectic form of Cn, And in this situation, the kth capacity for any k of the ball is the same, of the compact set, is the same as the kth capacity of its boundary, and it's an element of the action spectrum of the boundary as a contact manifold. Moreover, if B is convex, then the first capacity is actually the systole of the contact manifold, of the boundary. The systole is the period of the shortest closed Reeb orbit. Okay, this property fails. This property requires convexity in an essential way. There are counterexamples that can be made on non-convex domain. Okay, let me remind you the recipe for computing the capacities of solid ellipsoids. It's very classical. So consider the ellipsoid A1AM and consider its boundary. So the action spectrum of the boundary is the set of multiples of the parameters AJs. Now let's enumerate the spectrum in increasing order. I'm gonna call each element by sigma 1, and sigma 2, sigma 3, and so forth, strictly increasing order. And now let's write down this sequence of sigma j by repeating every sigma j according to a certain multiplicity. So I write down sigma 1 d1 times, and I write down sigma 2 d2 times, so on and so forth. And the di is you can say it's the number of, parameters ai that divides sigma j. Sorry, let me say it again. dj is the number of parameters ai that divides sigma j. Or if you want, if you take the space, the subspace of periodic orbits of period sigma j, that's a sub-ellipsoid, and it's a sub-ellipsoid of dimension 2dj minus 1. Now, the kth Eckland-Offer capacity is the kth element on this sequence. There may be repetition, some ck may be equal to ck plus 1 if there are, say, if there are non-isolated closed Reeb orbits. So our second theorem, which was really our goal, gives a recipe for computing the Eckland-Offer capacities of Besse convex contact spheres. And it tells us that the recipe is the same as for ellipsoids. Maybe you enumerate, so you have a Besse convex contact sphere, you enumerate its action spectrum in strictly increasing order, sigma 1, sigma 2, and so forth. Then you write down this list by repeating every sigma j according to a multiplicity, and the multiplicity is the same as before. So you take the subspace of sigma j periodic orbits. We know it's actually an integral homogeneous sphere. In particular, it's connected. Its dimension is 2dj minus 1, and the dj is the multiplicity of sigma j. Okay, so with this, ck of y is the kth element in this sequence. And this follows pretty much from the fact that Clark action functional is perfect, and it follows from knowledge of how the index behaves for Besse contact manifolds, which again is symplectic linear algebra. So the non-trivial part was the perfectness of the function. There's a further ingredient that is the fact that the Eckland-Offer capacities of convex stuff can be computed by means of the Clark action function. I don't know if that's possible for general convex spheres, but for Besse convex spheres, it's possible thanks to the fact that the function is perfect. Okay, I won't say much more on this because I prefer to switch to the second part of the talk. Are there questions?
Can you give an idea of how you prove perfectness?
Oh, how we prove perfectness? Yes. Yeah. So very rough. So the fact that a sphere is convex tells you pretty much that that the Morse index of the Clark action function at the critical point is essentially the Maslov index up to a normalization. Convexity tells you that so the Maslov index computes intersections with the Maslov cycle in the symplectic group. Convexity tells you that in the symplectic group you pretty much rotate always in the same direction. So yes, as you go through an orbit, you pick up more and more index. You never, for instance, indices are all positive. So we know how the index behave very precisely. Now, I want to do pretty much 90% of the proof consists in showing that the rational homology of every critical manifold, the S1 equivariant, rational homology, is trivial in odd degrees. Once you have that, there are no possible cancellations because the Morse indices are all even. And for proving that, it's a torsion argument. If there's a cohomology in odd degree, you produce some unwanted torsion in the S1 equivariant cohomology of the domain. It's a bit of a tour de force, but the general idea is simple, and the details are a bit messy. But this is more questions on this? Yeah. So okay. So I actually don't know if the two previous theorem holds for, say, non-convex Besse contact spheres, say fiber star-shaped sphere, Besse spheres in CN. I don't know.
Could it be that Besse contact spheres are automatically convex?
Convex is not very symplectic, right? So yeah. So it's not even known if there's an exotic Zoll sphere. So people feels, I don't know if Alberto has ideas on that, but yeah. So okay, second part of the talk, which is another property of Besse convex spheres, this is the part which is joint work with Alberto and Christian Lange. It was motivated by the classical Viterbo conjecture, convex symplectic geometry, and actually from a generalization of it that one could formulate, say, relatively easily. Let me remind you first the conjecture, although most people here know it. So Viterbo conjecture that goes back, if I'm not wrong, to the year 2000 or around 2000, says that every convex body C in CN has systolic ratio, which is bounded from above by 1, with equality if and only if the convex body is symplectomorphic to a round ball, say, of the same volume. So the systolic ratio here is the quotient. Alberto already mentioned it, but it's I use a different convention somehow. I take 1/n, what Alberto defined. So it's the quotient of the first capacity, first Ecklanhofer capacity of the convex body, which is the systole of it's the period of the shortest Reeb orbit on its boundary, modded out by the volume of the convex body to the power 1/n, where n is the dimension of the complex dimension of the symplectic vector space in the ambient. So this conjecture is widely open, although it's known that there's an upper bound which is independent by the period due to work of Arstein, Avidan, Yaromostrove. And so now let's, so our work was motivated by the following remark. So let me first introduce what I call here the kth capacity ratio, which is the same thing as the systolic ratio in Viterbo conjecture, but for the CK capacity. By the way, Viterbo's conjecture is phrased for any capacity. And indeed, there's a harder conjecture that says that all symplectic capacities coincide on convex bodies. But so for me, let me stick to the Ecklanhofer capacities, at least for this generalization. So our work was motivated by the following remark. So I denote by rho k of a convex body C in R2n, what I call the kth capacity ratio, which is the quotient of the kth Ecklanhofer capacity of C, quotient by the volume of C to the power 1/n. Once again, n is the half dimension of the symplectic vector space. And now here are two remarks, which are pretty much a combinatorial exercise. There's not really a symplectic geometry for proving them, but they looked intriguing just to us. So first remark is the following. So consider the function, so it's well known that Viterbo's conjecture holds, say, on the subspace of ellipsoids. So if all the convex bodies you consider are ellipsoid, then this conjecture is very, very easy to prove, because for ellipsoids, everything is explicit. So here's the situation for the higher capacity ratios on the space of ellipsoids. So I'm going to consider the capacity ratio of rho k on the space of solid ellipsoids. And first remark is that the local maximizers of these capacity ratios are those ellipsoids which are rational ellipsoids, so they're Besse. And if the parameters of the ellipsoid, we call them as usual A1, AN, then of course they will have a common multiple, and there exists, say, minimal positive numbers, positive integers, Ri, such that R1A1 is equal to R2A2 is equal to R3A3, and so on and so forth, up to Rn AN. And so a local maximizer is an ellipsoid, so that the AI have such associated Ri, and these Ri are positive integers, such that their sum, R1 plus R2 plus Rn, is equal to k plus n minus 1, where k is the k of the capacity that we consider, and n, once again, is the number of parameters, the half dimension. So somehow, in vitro Ball conjecture, the Zoll ball played a role, and here the Besse ones play a role, the Besse ellipsoids play a role. The second remark is is for global maxima. Now, the same function, the kth capacity ratio, its global maximizer are certain rational ellipsoids, which look like the following ones. So if the k of the capacity, you write it as, in this way, as Qm plus a remainder, R. It's not actually a remainder because I want R to be always positive. So this is the definition of Q. So if you write K as Q times N plus R, then the global maximizer, the global maximum of the kth capacity ratio on the space of ellipsoid is given by this expression. The expression itself is maybe not so relevant. Let me read it anyway. So it's Q plus 1 to the power N minus R plus 1 mod N times Q plus 2 to the power R minus 1 mod N. It's not very nice as an expression, but the global maximizers, they look nice. They're rational ellipsoids in which the parameters are divided in two blocks, and in each blocks they're all equal. So AN is equal to AN minus 1, equal to backwards equal until AR. So this is the first block of parameters. Second block of parameters are the remaining ones. Say AR minus 1, which is equal to AR minus 2, which is equal to so on and so forth, A1. And this is Q plus 1 mod Q plus 2 times the other parameters, AN. So this is intriguing. It shows that there are rational ellipsoids that have a distinctive property. Still don't really know what to do with this, but at least prompts us to ask the following question, to generalize a vitro Ball conjecture, and say, I phrase it as a question, I have no idea. I wouldn't dare to phrase it as a conjecture, there's nothing known. So the question says that given a convex body C in R2N, is it true that the kth capacity ratio of C is bounded, strictly bounded from above by the same maximum that it achieves on the space of ellipsoids, which I gave before, with equality, and this maximum is achieved, is it true that this maximum is achieved precisely at those convex bodies that are symplectomorphic to the, say, rational ellipsoids of remark 2? Or maybe there are exotic Besse convex spheres, I don't know. But maybe they have similar strata. Maybe the strata have similar properties than the Besse ellipsoids of remark 2. So once again, let me point out this is a difficult question because for k equal 1, it's vitro Ball conjecture. But this is as hard as vitro Ball conjecture. So of course, there's not much I can say on this, otherwise the title of the talk would have been different. So let me mention that Peter-Bose conjecture, there are some positive results on Peter-Bose conjecture on a local version of Peter-Bose conjecture. So I'm going to mention here two theorems. I start from the second, actually. So the second, which is the most recent one, is due to Alberto, Abbondandolo, and Gabriele Benedetti. It says that the round balls are local maximizers of the systolic ratio defined on the space of convex bodies in R2N. And when I say local maximizer, I put a little star to explain it. I mean local maximizer with respect to the C3 topology on the space of convex bodies. So this is true in every dimension. And in dimension 4 was proven before by Abbondandolo, Brown, Renievich, and Salomao. And the statement is slightly stronger in dimension 4, as far as I understand. It says that, it actually says that the local maximizer of the systolic ratio on the space of convex bodies on R4 are precisely those convex bodies symplectomorphic to a round ball. So it's a So both theorems follow from contact systolic statements, and this is a recent, say, relatively recent business that started with, if I'm not wrong, with Alvarez-Paiva and Balashev, and it culminated with the theorem that I wrote down here of Alberto Abbondandolo and Gabriele Benedetti. Alberto spoke about it on Tuesday in Lisbon, so some of you might have listened to it. So let me introduce the theorem. I'll go with time. Okay. Here it says the following thing. So you have a close connected contact manifold of dimension 2n minus 1. So I call it Y, contact form lambda. And let me call tau 1 of lambda the systole, what before was the first capacity. But here we're not on a convex, we're not talking about convex spheres. This is a general contact manifold. So tau 1 or lambda, once again, is the systole of the contact form, namely the period of the shortest Reeb orbit. And I'm going to denote as before by rho 1 of lambda, the systolic ratio, which is the quotient of the systole by the contact volume of Y to the power 1 over n. And this theorem of Alberto Abbondandolo and Benedetti, which is really the final theorem that came after many partial results. So in particular, also full results, but in dimension 3. So this theorem says that the C3 local maxima of rho 1 are precisely the Zoll contact forms. And in dimension 3, it's also known that, as already mentioned, Zoll, oh, yeah. Okay, so other questions on the settings? Okay, so now our goal for this second part of the talk was to characterize Besse contact forms on, say, contact manifolds in general as local maxima of suitable, say, higher systolic ratio. So the terminology is not stable yet. This is probably not a good terminology because systole really means, say, the shortest period. And, but let me introduce the ratio that's relevant. So we can achieve this goal to some extent in dimension 3. And this is the statement that I'm going to give. Yeah, I didn't mention all the contributions. So as I said, this theorem is the culmination of a series of results. In dimension 3 was first proved for spheres by the 4 authors I mentioned before, Abbondandolo, Brown, Renievich, and Salomao. And then it was extended to all 3-dimensional close contact manifolds by Gabriele Benedetti and Jung-So Kang. I should have written it, sorry. Yeah, so the characterization of Besse contact forms that we could find goes as follows. So let me introduce the relevant ratio. So I have a 3-dimensional close connected contact manifold, and I denote by tau k of lambda of this contact form the quantity that is defined here, it's pretty much the kth element of the spectrum. But let me be more precise. Tau k is the minimal tau, such that there are at least k periodic orbits with period and most tau. And when I say that there are k periodic orbits at least, I count iterates of the same periodic orbits separately. Okay, so this is in formulas, it's what I wrote here. Now I denote the kth systolic ratio, we can call it, or by rho k of lambda. And this is, as you can imagine, the quotient of tau k of lambda by the contact volume measured with lambda, square root of it, square root of the contact volume, so that if you, as usual in this business, if you rescale the contact form by a positive constant, the ratio is unchanged. Hopefully the definition is clear. So now, assume you have a Besse contact free manifold, then we know that there's the rep flow is periodic itself, and I'm going to call k bar of the contact manifold the minimal k such that the associated tau k is the minimal common period. Okay, so since we are in a Besse contact manifolds, then the situation is, so all the tau k will be equal to tau k bar for k is strictly larger than k bar. And for lower k, we have smaller values. So first a remark, which is rather straightforward. It says that if you have a local maximizer of this kth systolic ratio, rho k, then the contact form at the local maximizer is necessarily a Besse contact form. And its k bar is at most k. I don't know if it's equal to k. It is equal to k if the manifold is S3, because if the contact manifold is S3, a Besse S3 is a rational ellipsoid, and things are very explicit. So to prove this remark, if you assume that this remark doesn't hold, then you can find a point in your manifold. So either the manifold is not Besse, or it's Besse, but its k bar is larger than the k that you used for the systolic ratio. And you pick a point that is either in an open orbit or in an orbit that has a longer period than the tau k. And you can just modify a little bit the contact form around that point, lowering the volume or without touching the rho k. So it's rather straightforward. So the Besse contact forms come up as local maximizers. What's non-trivial is the opposite statement, which generalizes the result of Abbondandolo and Benedetti. It actually, since it's dimension 3, generalizes the result of Benedetti and Jung-So Kang. So the theorem says that if you have a 3-dimensional Besse contact manifold, and you consider its k bar, I just call it k from now on. So k bar, once again, is minimal k, such that tau k is the minimal common period. So we consider that k, and there exists a C3 open neighborhood of the Besse contact form. I call it U, the neighborhood, such that the kth systolic ratio of any contact form in that neighborhood is at most the systolic ratio of the original Besse contact form, and it's and this inequality is an equality if and only if the two contact forms, lambda and lambda 0, are strictly contactomorphic. So there's a dphi of y that pulls back one to the other. Okay, so this is the statement, and I believe I have some 12 minutes left. I'm gonna quickly sketch the proof. Unless there are questions on the statement. So the proof builds on the proof for Zoll contact manifolds of Gabriele Benedetti and Jung-So Kang, and also, I mean, the business was started by Abbondandolo, Brahman, Vignevich, and Salomao, say for S3. But there's further difficulty because Besse contact manifolds are more complicated than Zoll ones. So here are vaguely the steps. Hopefully I have time to complete them. So start with our Besse contact manifold, Y with the contact form, Besse contact form Y lambda 0. And I consider the relevant K, which is the minimal common period. And without loss of generality, we can set this to be equal to 1. Now let's take lambda, which is C3, which is another contact form of Y3 on Y, which is C3 close to the Besse contact form Y0. And there are a few issues with the quantifiers. One has to be careful, but for the purpose of this talk, I just ask you to believe me that the quantifiers work out well. So I have this lambda, which is C3 close to lambda 0, and without loss of generality, meaning up to multiplying it, up to rescaling it with a constant that's close to 1, I can assume that K of this lambda is also equal to 1. Yeah, I'm already using a little bit of information about Besse contact-free manifolds here. It's just the fact that the Besse contact-free manifold has the regular orbits that have common period, and the orbits that have smaller period are isolated non-degenerate closed Reeb orbits. Thanks to the Morse-Bot property that I mentioned before, for instance. Now, once we have our two contact forms, which are C3 closed and normalized so that they have the same K, it remains to show that the volume of the new contact form measured with the new contact form lambda is larger than or equal to the volume measured with the Besse contact form lambda 0. So, yeah, so next step, without loss of generality, I can assume that, so we know that the contact form lambda has a one periodic orbit, the one that carries this value K. And this one periodic orbit will be closed to some periodic orbit of the original Besse contact form. And now up to pulling back everything with a diffeomorphism, which is say C1 close to the identity, I can actually assume that the two contact forms lambda and lambda 0 share a same one periodic Reeb orbit, which I'm going to denote by gamma. Okay, so there's a bit of work here that one has to be careful with the quantifiers, but it can be done. Now, this gamma here, again, it's a common one periodic Reeb orbit for lambda and lambda 0, but it may be the iterates of a Reeb orbit of smaller period. So I'm going to denote the period by its minimal period by 1 over m, some integer m. And I have to keep track of this parameter somehow. Now, the core of the proof and the novelty was that on a Besse contact manifold, given any closed Reeb orbit, there exists a quotation mark global surface of section that has boundary on these orbits. Global surface of section for the Reeb flow, for the Besse Reeb flow, with boundary on the given Reeb orbit. So I put quotation mark here because it's not really, what we have is not really a usual global surface of section. It's almost a global surface of section, except that you covered the boundary a multiple number of times. So basically, this object is a smooth function from a compact surface with boundary, which I call sigma, into our contact manifold Y. It has these three properties. So first property is that this map F is an embedding when restricted to the interior of the compact surface with boundary. And it's an embedding into the complement of the given periodic orbit gamma in the Besse contact manifold. And this embedding is a transversal to the Reeb vector field of lambda 0. And moreover, every regular Reeb orbit of the Besse contact manifold, namely every Reeb orbit that has minimal period 1, intersects the image of this embedding in Q points. And Q is a parameter that I have to keep track of. So the statement here is that Q is the same for all the regular orbits. So I mentioned that sigma is a compact surface with boundary. The boundary can possibly be disconnected, but the restriction of F to the boundary of sigma is a covering map of the periodic orbit gamma. And I'm gonna denote by P the number of sheets of this covering map. Actually, to be more precise here, every connected component of the boundary of sigma is a covering map of gamma of the same number of sheets. So number of sheets is the same for one component. So third property is tells us how to relate the parameters that are introduced so far. P, Q, and there was another parameter that I remind you. That was M. That was the number of times that gamma was iterated to in order to get to the common period one. So on a Besse contact manifold with common period one, it's well known. It's been I believe it appears in a recent nice paper of Lange that the contact volume of the Besse contact manifold is the same as minus the Euler number of the Besse contact manifold seen as a cipher fiber space. So if our Besse contact manifold is a Zoll contact manifold, this is the usual Euler number of the manifold as a circle bundle over the space of orbits. And here there's a generalization of that. We don't have a nice circle bundle, we have a cipher fibration, but there's a notion of Euler number, which is analogous somehow. And now the Euler number, by the recipe that we have for constructing this surface of section, minus the Euler number of the Besse contact manifold is given by the three parameters that we introduced. It's P mod M times Q, where once again, P is the number of sheets of the covered map, Q is the number of intersections of the surface of section with a regular orbit, and M is the multiplicity of the orbit gamma that we consider. Okay, I have 5 minutes and 3 more slides. We'll see, maybe I will not tell the full story, but almost. So whenever you have a global surface of section, that gives you an open book decomposition of a contact free manifold. And so we have the same here, but I put open book decomposition in quotation marks because we rather have a covering map. So construction is the following. I take the product of my surface sigma, was the surface of section, with S1. S1 is the one periodic circle. And I remind you that 1 was the common period of the Besse contact manifold. And I lift the surface of section to a map for sigma times S1 to Y. And this map sends a pair Z comma T into, so first you map Z into the image under the global surface of section, F of Z, and then you flow with the Besse rep flow for time T. Okay, so this gives you, so if you restrict this map to the interior of sigma times S1, you get a covering map with P sheets of the complement of the periodic orbit gamma. And this is actually the contact manifold that I'm gonna work in from now on. So I pull back lambda 0 by the map F, and I call the pullback mu0. It's a contact form on this product. And I denote by mu0, it's Reeb vector field as usual. And the Reeb vector field by construction is just d over dt. So, okay, now let's take the second contact form lambda, which is C3 close, I remind you, to lambda 0. And I remind you also the gamma was a common periodic orbit of lambda 0. So now I take this product sigma times S1 and I equip it with a pullback of the contact form lambda, which I'm going to call mu. Now, now this is again a contact form on the interior of sigma times S1. Its Reeb vector field, which is defined in the interior, is C1 close to the Reeb vector field of the Besse form. So it's C1 close to the vector field d over dt. And it extends smoothly to the closure of this product. And therefore, since it extends smooth and it's close to d over dt, I can consider the first return map to the section sigma times 0. So I'm gonna call the first return map tau. sorry, the first return time, I'm going to call it tau. So this is the time it takes a Reeb orbit to flow from a point on sigma times 0 back to sigma times 0. With the first return time, I construct the first return map as usual. So this is I call it sigma. It's a diffeomorphism of sigma. I've lost power. So I think it's a record. So I call this map sigma. And so the first return time is C1 close to the constant 1. And I'm going to call sigma, it's different. And the first return map is C1 close to the identity. So the proof is almost over. Now, now let's consider the restriction of mu to the section sigma times 0. This is a contact form in the interior of sigma, but it degenerates on the boundary. And now the first return map, as usual in scattering theory, the first return map is an exact, sorry, what did I say? Let me rephrase. So I take the restriction of mu to sigma. Sigma is a surface. And the differential of mu is now a symplectic form on the interior of sigma. I said contact form before, sorry. Symplectic form on the interior of sigma. And it's not symplectic in the closure, it degenerates in the closure. The first return map is actually an exact symplectomorphism with respect to the primitive nu of this symplectic form. So phi star nu minus nu is the differential of tau, where tau is the return time, which is the same as the differential of sigma, difference from tau and 1. Okay, now one last thing, and I'm really done. I have only 1 minute left. Let me integrate. So this final part of the proof, well, beyond the construction of the global surface of section, the proof is really following what the analogous proof for Zoll contact forms for the Zoll results of Alberto and collaborators, and then Gabriele and Giusto Cami. So if I integrate now this expression, this equality, with respect to d nu, I have the integral of sigma, which is equal to the integral of tau on d nu plus the integral over sigma of d nu. So the first term, if you integrate the first return map of a global surface of section, you obtain the volume of the ambient contact manifold. But remember that here, this first return map is actually a qth return map in the contact manifold, because we had a covered map. So the first integral gives me q times the volume of the contact form, of the contact manifold y lambda. And the second integral by Stokes is just the integral of nu on the boundary, which is the period of the periodic orbit gamma, and except that sigma covers the periodic orbit gamma p times. So this integral gives us number of sheets p divided multiplied by the period, which was 1 over m. And now this p over m is nothing but the volume times q. So conclusion, the integral of this function sigma is q times the difference from the volume measured with lambda and the volume measured with the Besse lambda 0. And finally, if this difference of volume is negative, which contradicts what I want to prove, then we have that the integral of sigma is negative. And I went a little bit too fast on my slides. I forgot to mention this condition, but sigma takes a precise volume on the boundary. It's given by the integral along a short path from a point to the image of the point under the return map. Thanks to this normalization and the fact that this integral is negative, there's a fixed point theorem that's pretty much it's a slight generalization of a fixed point theorem of Benedetti and Kang. This implying that there is a fixed point of the first return map with negative value of sigma. Negative value of sigma means that the tau of the fixed point is strictly less than 1. 1, I remind you, was tau k, but the function tau is actually very close to 1. And therefore, tau is larger than tau k minus 1 of lambda. So Now, this fixed point of the first return map gives us a periodic Reeb orbit of the contact form lambda, and its period, it's contained in the open interval from tau k minus 1 and tau k, which is a contradiction because the tau k enumerates the element of the action spectrum. So I was a little fast on this, but yeah. So I can answer questions just in case. Otherwise, I can stop here. Sorry for being over time.
Thank you very much. Questions, comments? Well, I have a question. So regarding the original form of Viterbo conjecture, yes? Like to me, I try to think of ellipsoid of given volume, but then I need to make it skinny, and then I imagine that there must be this characteristic which is short, right, on the common ring. That's my picture that I have in mind. Do you have some intuitive picture for your generalization to ellipsoids?
No, to be honest, no.
I don't know.
No, I don't know if I'd like to ask something on that, but no.
I mean, I understand the evidence and the starting point.
Yeah, the evidence is for ellipsoids. No, no, not much, unfortunately. Not really, yeah.
Further comments? Well, if not, let's thank Marco again.